Okay, welcome back everyone. Today is Wednesday, June 23rd. Okay. So here is updates. Okay. So I posted class examples done by computer software, which is example 411, in which we did it yesterday. I have two versions. One is 411 done by PTC Mascad or SMath Studio if you want to download and use free version. Okay. Or this is example 411 done by Symbolic Math Toolbox with Live Editor. Okay. And then this is class example 412 also. This is done by MATLAB Live Editor Symbolic Math Toolbox. Okay. This is actually, this problem you can do it by hand actually if you want to, but this is an example of a solution done by a software. Okay. So today we are going to take a look at Unit 4B, the last unit of the ES201 statics. Moments of inertia. There are a few class examples. Actually, I also used MATLAB Symbolic Math. Okay. I just posted here, so please take a look. Okay, by yourself. So today we are going to get into Unit 4B, moments of inertia. Here's before I start today. If I finish up this unit today, tomorrow there's no class. I basically turn it into study day for the final. Okay. So, anyways, but if I cannot finish up, of course you have lecture tomorrow too. So.
We have quiz tomorrow.
We have a quiz tomorrow. So okay. So don't worry. So I'm not gonna try to finish up. So, but tomorrow is like, if I complete almost all lectures today, tomorrow I guess you show up, take the quiz, go home early. That's what happens. Okay, that's right. So let me double check. Okay, tomorrow we have class because we have quiz. Let me repeat. You have to show up tomorrow, no matter what, because tomorrow is a quiz day. Okay. Because this is going to be recorded. Okay, double check. So, moment of inertia, let's just get in. Moment of inertia. This is one of the subject that when I took this class, I had no clue what the teacher was talking about. Moment of inertia, what the heck is that? I have no idea what you're talking about. Well, moment of inertia, the term actually confuses students. Moment of inertia, the terminology is, same terminology is used for two different areas. One is mechanics, which is essentially dynamics, spacecraft design type of thing, something called mechanics. The other one is structures, structural mechanics, engineering structures, those kind of things. So same terminology is used like a slightly different meaning or usage of application. So that is the main source of confusion I realized later on. So today I'm going to use the term moment of inertia. I'm going to actually, since this is a structural mechanics type of class, if somebody says moment of inertia, it's called area moment of inertia. Okay. So this is basically structures. Since this is engineering mechanics, and then after this class, you're going to take solid mechanics, and then solid mechanics is going to lead you to structural analysis. So this is essentially structural analysis term, area moment of inertia, and then people actually oftentimes use the same word in slightly different meaning. That's called mass moment of inertia. So this is actually, origin is the same and concept is the same. However, this is actually spacecraft design, typically. not only spacecraft, but same different kind of application. One is essentially if you're looking at the cross section is area. Suppose if you pick up a wood, okay, there's a river here flowing, and then you want to make a bridge, and then, oh, I found the wood plank. So, okay, well, this is the wood. So I'm going to make a bridge like this. Oh, okay. Then people start walking on top of the bridge and then realize in the center of that bridge, and then, wait a minute, this is really bending. Is it really okay? I may collapse it. So, ooh, okay, so if so, let's just do this way. I'm going to use this bridge this way now, and then you can instantly tell, hey, this is much more stronger, stiff. It's a stiffer bridge. So suppose if you apply the force, okay, right here and right here, this force is trying to bend this material. So especially in the center of this material, you have a maximum bending moment applied. Of course, you can draw a shear moment diagram for this thing, which is kind of simple. So you realize, hey, this is the maximum moment developed in the center, right here, and right here. And obviously, this is much, much stronger, resistive against that bending moment. Why is that? Well, it's the same wood. You just rotate the direction. What is the big difference between those two? The difference is moment of inertia. Okay, so how much area is distributed away from the centroidal axis so that you're going to resist the bending, which is maximum bending occurs at the center of this material. So that's why, you know, what is the optimum solution for this? If you are a serious engineer, you're going to, okay, I'm going to pick up an I-beam or something, this kind of thing, and then make a bridge out of that. This is the cross section, and then I'm going to make a bridge out of this. This is probably the optimum solution. So if this is a 1, this is a 9 times stronger, this is probably 30 times stronger. Resistive against the bending moment, which is the loading you are going to take for this structure. What is the difference? The only difference is the cross section. So cross section, the property of cross section is quite important when you analyze, especially in this case, bending moment. So this is called moment of inertia. So we are going to understand moment of inertia being a property of cross section, which is typically used for structural analysis. That is the area moment of inertia. So we oftentimes use the specific term area. Now, when you go to spacecraft design, you know, you basically branch out the discussion. Actually, you're studying moment of inertia here in this class. It's the same concept, of course, it's the same equation and everything. But moment of inertia, as a being a property of area, is going to be used for structural analysis. But if you go to spacecraft design, I guess there's another different things or application you have to think about. In other words, moment of inertia could be a property of mass. In other words, how much mass is distributed for this body. Now, that is quite important because when you design a spacecraft, you attach a thruster and then spacecraft starts spinning in this direction. And then you want to all of a sudden change it to this direction, how much thruster required. That is essentially resistive against the changing the direction of spinning. That's called mass moment of inertia, which is kind of similar concept. Actually, the conceptually speaking, all the same equation, but the application was slightly different. And then the terminology is the same. If somebody says moment of inertia, it could be area moment of inertia or it could be mass moment of inertia. It is totally different application, so that actually confuses you. Okay, so I'm going to actually pick up a little bit of mass moment inertia later to kind of highlight the reason why moment inertia is being used. But let's just consider this is area moment inertia to begin with. Let's just be careful about area moment of inertia. Okay, so by definition, area moment of inertia can be given by integral of x squared dA. It's just the area, so how much distance is away from the area. Now, if this is mass, moment, inertia, obviously, instead of area, you're going to use the distributed mass of a body. Okay? So how much mass is concentrated away from the centroidal axis is going to give you a tendency of how much rotation you can expect. Suppose if you create a spacecraft with this kind of small, tiny body. If you push it, spin like this. However, if you have this kind of arm, very heavy things attached to it, if you spin, it's going to spin like crazy. Oh my goodness. Because what's the difference between those? Well, mass, moment, inertia. Okay? So anyways, so let's just concentrate on area moment inertia for a moment. Okay? So oftentimes, this is called the second moment of an area. Have you ever seen this? This is the first moment of the area. First moment of the area was used to determine centroid. Is that right? We use this for centroid. This is basically distance multiplied by the distributed area at that point that actually create the moment about given axis. This is first moment of the area. Now, if the area is a square term, it's going to call second moment of the area. This is called moment of inertia. Okay. So obviously, the unit is arranged to the force power. Okay. So let's just take a look at it. So this is an arbitrary area given on xy plane. So this area has a certain property. One of the property is, of course, moment of inertia. So how much moment of inertia do you have for this area? So you're going to choose a small tiny area dA at just about any location of this cross section A. So this dA has a distance x away from y-axis. This area is distance y away from this x-axis. Take a square of it. That's called moment of inertia of this dA. It's just how much distance away from this area from a given axis. Okay? So obviously, if this dA is really, really far away, it's going to be a larger moment of inertia. That's exactly what I'm talking about. So this is the center line. So area is essentially concentrated away from the centroidal axis. That's why it's higher moment inertia, obviously. This one, almost all the area is distributed around centroidal axis. So it doesn't have much moment inertia. So a big difference between this and that is huge difference in moment of inertia, obviously. Okay. So that's moment of inertia. So how much distance away? That square is going to be a moment of inertia. So what is the moment of inertia of this entire area, cross-section area? Obviously, you integrate. You integrate to get it. So this is, by the way, definition of the area moment of inertia. Very simple. Okay. Now, area moment of inertia, this is the moment of inertia about the x-axis. In other words, how much moment of inertia you can have measured relative against x-axis. This is Ix. This is the moment of inertia. How much do you have measured relative against y-axis? This is moment of inertia of y-axis, Iy. Okay. So this is moment of inertia about x and y-axis. This is 2D plane, obviously. However, you have z-axis. Okay, z-axis. Z-axis is right-hand rule. So z-axis is actually coming out of that paper or surface. So if you take the moment of inertia about the z-axis, this is called polar moment of inertia. Okay, z-axis or pole. So this is called polar moment of inertia. Okay. So polar moment of inertia is instead of taking x or y, you're taking r, because r squared is equal to x squared plus y squared. So r squared dA, r squared is x squared plus y squared. So basically, polar moment of inertia is a combination of those two. This is called polar moment of inertia. So polar moment of inertia is polar moment of inertia is basically a combination of moment of inertia about x-axis added together with about y-axis, both combined. Polar moment of inertia is typically important if you have something like a shaft, which is a rotating body, axis symmetric body. So such as you're dealing with, okay, well, this is the shaft, cross-section circle, okay. Then you're going to actually twist it, okay, applying torque, and twist it. Is this shaft strong enough against that twist? Well, obviously the cross-section is an issue. So is this a big enough cross-section to take that twisting torque within the limit of internal shear stress developed? What you need to look at, of course, polar moment of inertia. That is a cross-section property of this kind of body. Okay. Torsional resistance. And then obviously, this is a bending resistance. This is the moment of inertia about y-axis, x-axis. Obviously, moment of inertia about x and y-axis is different. That's why those two are different in resistive against bending moment, obviously. Okay. All right. This is actually quite important. Moment of inertia for a standard shape, such as, suppose you're given rectangular shape, or suppose you're given completely circular cross section. These are the standard shape, not like this arbitrary shape. Okay. Now, in such a case, moment of inertia is well known about its centroidal axis. So obviously, if it's rectangular, this is a centroidal axis. Okay, so this is right here, centroid. Well, if it's circular cross section, this is a centroid, x and y, and x and y. So moment of inertia of this standard cross section, such as rectangular shape or circular shape, moment of inertia is given at the centroidal axis. Let me just give you that right now. Of course, it's already given in your note, but let me just preview and give you. So cross-section property of those, it's just listed. So if it's rectangular cross-section, obviously the cross-section area of this shape, let's say this is B. Let's say this is A. Cross-section area is B times A. Moment of inertia I. Did I say moment of inertia I? Yeah, I. Okay, I. Moment of inertia is I. So moment of inertia of I in about x-axis. Now x-axis goes through the centroid, so I'm going to call this IXC. Okay, so this is the moment of inertia about x-axis going through the centroid, IXC. This is equal to 1/12 B times A cubed. Moment of inertia IY of C. In other words, moment of inertia about y-axis going through the centroid. This is 1/12 AB cubed. Now, I'm going to cover something called cross product of inertia, IXY of centroidal axis. This is 0. Don't worry about this too much. I'm going to cover that. This is the cross product of inertia. This is a circle. okay? Obviously, the area, suppose if the radius is given, area is equal to pi r squared. IXC, which is exactly equal to IYC, this is a circle. This is given pi times r to the fourth power divided by 4. IXYC is again 0. Okay? So those are the moment of inertia for an area with a standard shape. These are very well known. Okay? So if the moment of inertia for an area is known about an axis passing through its centroid, okay? In other words, okay. In this case, those, okay. It is convenient to determine the moment of inertia of the area about the corresponding parallel axis theorem. Here we go. It's probably the most important term for this 4B, parallel axis theorem. Very, very important. So, for example, if this is rectangular shape, I know moment of inertia about x and y axis going through the centroidal. In other words, I know moment of inertia going through x prime, y prime axis. But what I want to know is moment of inertia of this area about x and y axis. X and y axis is not the centroidal axis. So you are going to determine moment of inertia of this cross-section or that cross-section given, already know, so about centroidal axis, and then bring it to either x-axis or bring it to y-axis to determine Ix or Iy. So if you know Ix prime, I'm going to use over bar, Iy prime over bar. So those are the local moment of inertia. So suppose you know local moment of inertia going through centroidal axis, in this case, x prime, y prime. But what I want to know is those, Ix and Iy. How can we do such a thing using parallel axis theorem? So let's just take a look. So what is the parallel axis theorem? Okay, so parallel axis theorem is, okay, you are going to actually moment of inertia of dA about x prime axis, you have to find out first. So moment of inertia about x prime axis is basically dA is located, measured from x-axis, dy plus y prime, right? dy plus y prime. So this thing square is going to be dix. So you're going to integrate this and then determine that two components shows up. One of the component is this component. Wait. Those two together is Ix prime. So this is the moment of inertia about centroid. And then this one, okay, so those two is Ix prime over bar. And this, A times dy squared. dy is the distance measured from x-axis to the local centroidal axis x prime. So this much distance is shifted, so you are going to bring it back to the x coordinate to determine Ix. So parallel axis theorem is essentially given this equation. This is a parallel axis cell. So important thing is, okay, first of all, those are usually known. Local moment of inertia. Okay, so if those two known local moment of inertia is the moment of inertia about centroidal axis, you can actually describe it something like this. Ix is equal to Ixc plus Ady squared. Iy is equal to Iyc plus Adx squared. So this is actually a more commonly used form of parallel axis theorem. And then important information here is, obviously, if I say Ixc and Iyc, those are centroidal axis. Let's just zoom out, take a look. If you're talking about like a generic shape of area, such as rectangular shape or circular cross-sectional shape, you know the moment of inertia about the centroidal axis, Ixc, Iyc. Those are well known. So those are the known. So using those to determine the moment of inertia of a given axis by using parallel axis theorem. In other words, if the area is offset, such as, so this is x and y coordinate. Suppose you have a rectangular cross-section placed in here. This is actually x prime and y prime coordinate. Right here is a centroid. Okay? And then question is, okay, so determine the moment of inertia of this cross-section about x coordinate axis. How do you find it? You use parallel axis theorem because you know Ixc. Ixc is 1 over 12 b times a cubed. And then this is the distance dy. So Ixc plus cross-section area times dy squared is going to be Ix. In other words, this cross-section, if it bring it down to the x coordinate system, how much moment of inertia equivalent you can determine. That's parallel axis theorem. So you can use parallel axis theorem. You can determine any, just about any moment of inertia of any cross-section area located anywhere. This is probably the most important concept. You need to take it up from this unit. Okay, parallel axis theorem. Obviously, this is dx, of course. So if I would say determine Iy of this cross-section area, you're going to first determine Iyc plus cross-section area times dx squared. That's called Iy. Moment of inertia about this y-axis. Okay? Parallel axis theorem. You are going to probably use it all the time in solid mechanics. Okay. So next page, just a little bit more information. Sometimes after you determine moment of inertia, you want to determine radius of gyration. This is actually confusing me. Radius of gyration of an area is oftentimes used for the design of columns. Again, the terminology comes in from spacecraft design. Suppose if you design the spacecraft with a mass distribution this much. Radius of gyration is, okay, suppose if all the mass is concentrated in here, it is going to create the same amount of moment of inertia of the original design. So how much radius is it? That is going to basically characterize how easy to spin your spacecraft in certain direction because of the distribution mass is given by the mass moment of inertia. So that's the radius of gyration. So the terminology is originated sort of from spacecraft design, so it's kind of difficult to kind of visualize in structural analysis. But radius of gyration is kind of similar concept. So suppose if you just concentrate the area on certain distance away or radius away from the centroidal axis, how much radius do you expect to produce the same amount of moment inertia? Okay. So this is going to show up later in structural analysis. Now, at this moment, it's kind of hard to visualize because you are not ready yet, but you understand what is the radius of gyration. It's coming from moment of inertia concept. Okay. Now, moment of inertia for an arbitrary cross-section just like this, you have no choice, but you have to integrate. So there are some areas given. Then if I ask you to find out moment of inertia for that given area, this area is given as a function, either a function of x or y. You're going to literally integrate mathematically to determine moment of inertia. So there are two different kinds of problems you're going to deal with. One is this kind of problem. You know, I give you area. Area is described by this mathematical function, determine moment of inertia. You can do that. It's just basically it's very simple integral. The other one is a composite. This is an I-beam created by this shape, that shape, this shape. What is the moment of inertia of this, about the centroidal axis? First of all, where's the centroid? Okay, well, this is a centroid. So measure from there, what is the moment of inertia? You can do that. Okay, go ahead.
dA will be y times dx.
Ix is what?
The dA
D
will be y times dx.
dA is dA could be dx times y or dy times x, either way. In other words, taking, in this case, moment of inertia Ix is integral over the area. Integral over the area is this whole area, but you can integrate either in x direction or y direction. In other words, you can take dA this way. This could be dA.
Or as if you go for the IY.
That's for, yeah, that's right. So this is dy. Sorry, what's your question again? I'm not.
You already answered.
So yeah, in case of Ix, yeah, that's right. You are going to take the y squared dA. dA could be dA in this case, right? Y times dx. That's the dA, right?
Yeah.
Y times dx. So integration could be in x direction, y direction. So integration in x direction is going to give you Iy. That's right. Integration in y direction is going to give you Ix. That's right. Yeah. Is that your question? I hope.
Yeah.
Okay, good. So let's just find out those things. Class example 431. Okay. Determine the moment of inertia of the area about the x-axis. Solve the problem in two ways. So you can solve this in two ways. Okay, so what you need is Ix, isn't it? So you want to find out Ix. All right, so you can determine two ways. A, having a thickness dx, and B, having a thickness of dy. So you can integrate in x direction or you can integrate y direction. I'm going to actually start with part B. I'm going to flip-flop the process. I'm going to start with part B. So let's just try to solve this problem having a thickness of dy. Okay. So I'm going to start with a sketch. So this is x coordinate. This is a y coordinate. and then area is given. I'm going to exaggerate a little bit. So this is area, functions given, y equal to 2.5 minus 0.1 x squared. So this is the function, y as a function of x. Okay. So I'm going to just carefully choose the arbitrary location y. And then I'm going to cut out very thin strip. This is a very, very, very thin strip. That is dy. Okay. And then you're going to basically zoom right in. So this is a strip, you just cut it out. This is dy. And okay, so this whole thing is, so this is y axis, and distance here and distance here at the arbitrary location y, this is x, this is also x. Okay. And right here, this is a centroid. Okay. So local centroid, as you see, this is x2, that y2, that this is a local centroid location right here, centroid. Okay. So important information here is, okay, since you're given y equal to 2.5 minus 0.1x, I'm going to basically multiply by 10, so you have 10y is equal to 25 minus x. X squared, sorry. Yeah, so. Eh? No, x is x. Eh? Yeah, x squared, sorry about that. Okay, so from here, you can determine x equal to square root. X equal to square root 25 minus 10y. So this is the functional relationship, x as a function of y. So in other words, as you go along this y coordinate, how much x changes. In other words, this is going to determine this x and that x, both. And obviously, this dA, this is a dA. Okay. Now this dA is 2 times x times dy. So mathematically speaking, this is 2 times square root 25 minus 10y times dy. Okay. So now I'm ready to go to determine moment of inertia about x-axis, Ix. Okay. So this Ix is obviously integral over the cross-section area y squared dA. This is integral in the direction of y from 0 to 2.5 feet. Okay, 0 to 2.5 feet. Y squared times this dA. dA is 2 times square root 25 minus 10y dy. So moving on, so this 2 goes outside of integral, so this is the 2 goes outside of integral. Integral from 0 to 2.5, y squared square root 25 minus 10y dy. Okay, now this is a mass. So what did I do? Did I do this mass? Did I do this mass? I think I didn't do this mass by hand, I suspect. Cross example 431. Okay. This is already, by the way, given to you in update page. So you can just basically take a look at it. So apparently I didn't do the hand mass. I used the symbolic mass. This is y equal to blah, blah, blah given. And then dix is, okay, part B. So this is x equal to square root 5 times square root 5 minus 2y. Dix is integration of dix in the range from 0 to 3.5. That's what I have. So 23.8. Okay. Anyways, so please take a look at it. This is already given here. Okay. So let's just go back. So this is a hand mass. If you do it by hand, it looks like this, but I actually didn't do it by hand. Okay. This is going to be equal to 2 times bracket minus y squared over 15, 25 minus 10y to the power of 3 over 2 minus 2y over 375, 25 minus 10y to the power of 5 over 2 minus 2 over 13125. What the heck? But anyways, 25 minus 10y over power of 7 over 2 evaluated from 0 to 2.5. Something like that. Then if you do such a mass, 23.8 feet to the force power. This is the moment of inertia. Okay? Like I said, I didn't do this kind of mass. I just used the software. So I would actually recommend you, explore symbolic mass toolbox since you have free access to it. It's part of your tuition, so please use it. Okay? So before we move on to part A, in other words, you can actually do the similar thing, but now having a thickness of dx taken and then integrate in the direction of x, you can do the same thing. But it's not as simple as this, because if you do such a thing, you have to apply parallel axis on it. Okay? So before moving on to part A, let's just scroll down a little bit. Scroll down a little bit more. This one, composite areas. So you need this information first of all. I already gave it to you, but so this is a standard cross-section, rectangle, circular, semicircle. This is triangle. So this is quarter circle. So if you're given these kind of standard cross-section area, centroid locations given, and then those are the moment of inertia in x and y direction about centroidal axis is also given. Okay, and also product of inertia is also given. Product of inertia, we're going to cover that a little bit later. So make sure you have this information in your hand before we move on to part A of this problem. Okay, let's just go back. Take a look at part A. Part A, determine the moment of inertia of this area about the x-axis. Solve the problem in two ways. Having a thickness of dx, let's just do it, okay? All right. So part A, I'm going to, let me just sketch out. So this is y-axis, this is x-axis, once again. So this is the mathematically determined shape. This is y equal to 2.5 5 minus 0.1 x, okay? And now you're going to choose arbitrary location x, and then cut out this small tiny strip, which is dx, okay? Okay. Now let's just zoom in. So now you cut out this kind of cross-section dA. This is a dx. This is y. Here is the centroid, local centroid, here, C. Okay, so this is x tilde, y tilde, local centroid. Okay. And obviously y tilde is, this is y tilde. So this y tilde is essentially half of y. That's what the location centroid is. This is a rectangular cross-section. So suppose if you take a look at centroidal axis like this. Okay? So this is x prime, y prime centroidal axis. And one thing I can tell is, well, you know ix prime over bar, isn't it? Okay? This is 1 over 12 BA cube. Okay? So this B is dx. This A is y. Okay? So you know that. So this is essentially, you can call this IXC also. Okay? So this is the local moment of inertia going through the centroidal axis, IXC, which you know it, 1 over 12 BA cubed, because this is rectangular cross-section. Is that right? So you're going to basically, how would you move on with? So how would you move on? You want to have dix is equal to, let's just apply parallel axis theorem. So this is going to be dix prime over bar. This is, by the way, IXC, because it's centroidal axis, plus dA times y tilde square. Okay, so this is those two parallel axis theorem. Okay. Since this is distance, okay. Right here is the centroid. Okay. Here is the centroid. So this is distance y tilde away from x coordinate. Okay. So this parallel distance. Okay, sorry. So this is y tilde. So this cross-section area is y tilde away from x coordinate axis. So that's why you have to apply parallel axis theorem just about any location of you take the differential strip dx. So if you want to move on, okay, so let's just move on. Dix is equal to, this thing is, of course, 1 over 12. B, which is dx. A, which is y. 1 over 12 BA cubed. That's what the local moment of inertia at the centroid. of this small tiny strip is, plus dA is what? Y times dx. Y times dx. That's what the dA is. Multiplied by this offset distance y tilde. Y tilde is half of y. Y over 2. This thing square. Do you follow that? This is dA. dA is dx times y. This y tilde is half of y squared. Okay. So anyways, if you move on, what happens? This is going to be, if you simplify it, you're going to have y to the cube over 12 plus y over cube over 4 dx, which is, you can simplify it to y to the cube of 3 dx. Okay. Now, y is a function of x. You have to plug in y as a function of x. So this is y equal to 2.5 minus 0.1x into y cubed here. So moving on, so this is 1 over 3, y equal to 2.5 minus 0.1x to cube dx. If you take a cube of this function, this is going to be 1/3 of minus 0.001 x to the 6th power plus 0.075 x to the 4th power minus 1.875 to the x of square plus 15.625 dx. So what is Ix you're going to integrate? Ix is integral over essentially x, okay, dix, in which 1/3 comes out, integral over the x equal to minus 5 to 5 of this whole thing, minus 0.001 x to the 6th power plus 0.075 x to the 4th power minus 1.875 x to square plus 15.625 dx. Obviously, I know what you're thinking. I didn't do this by hand. I'm just copying from software. Anyways, so if you go through all of those crazy mathematics, you should get the same value, 23.8 feet to the 4th. This is a moment of inertia. If you take strip dx and integrate in x direction. So there are two ways of integral. You can get the same moment of inertia Ix. Go ahead.
So for part B, we didn't use the parallel axis theorem because it was in line with the centroid.
Well, because if you take a dx is always, no matter where your location x is, dx strip is, unless it is right here on the y-axis, it is always not lined up. So you have to have parallel axis on,
So
always.
The local centroid is not at the same location as the actual centroid, the main centroid.
Because what I want is I want to have moment of inertia about this x-axis. That's what I want. Okay. And then each time when I take a local dA, small tiny dA, the centroid, I know the knowledge of local moment of inertia about this centroid of each small tiny area. But the centroid is not in x coordinate. You have to each time use parallel axis each time. That's why. Go ahead.
Is that y equals 2.5 minus 0.1x? Is that
Because this is minus 5, this is 5. So you are integrating from here to here.
Is that have a to the second power on the x, or is that?
Second power.
So in the original graph thing, it has y equals 2.5 minus 0.1 x to the second power. Is this one different, or?
Is this correct? First of all, yeah.
Or is that?
Sorry, x squared.
Okay. And then the answer for it is that b to the fourth power? Is that what?
This is, yeah, sorry about that. D. So this is square, and the whole thing is cube.
Okay.
Yeah, so there must be a mistake. Let me double check. Cube, yeah, this is square, then this is a square, this is cube. That's why 6 power comes up.
Gotcha.
Yeah, okay, sorry about that. Just my typo. So let me just double check here. So this is square. Sorry, I forgot the square. And this is cube. So this is square. This is square. This is correct, by the way. If you, yeah. You probably don't want to do this by hand anyways. So that's why I gave you a handout here. So this is example, what, 431. This is part A. I did everything using symbolic math. So this is a given function of y to begin with. Then dix is going to be just to plug in, then one certain cube. Then you're going to integrate that function, whatever it is. I don't know what it is, but integrate from the range of -5 to 5. Whoa, you get the value. So again, I didn't do any math. If you use software, that means you bypass all the math details. Sorry about that. But if you go through the math details, this is going to be like this. Nightmare math details. You can choose to go with it, but I think I always argue about, you know, I'm not a mathematician. I don't need to know those details. I just bet the software does. Okay. Anyways, but don't forget, let's be very careful about setting up equations. As long as you set up the equation, the rest of it, you can do math details using software. That's fine if you want to. Go ahead.
Will we get like on our final a question from chapter 4?
Yeah.
So like, how are we gonna do that if we're not able to use the software?
I will probably not going to give you this kind of problem because it involves unnecessary bulky math stuff, which is nothing to do with this class anyways. But I guess the point I'm trying to make is you have to handle this math anyways, either by hand or by using software. I choose to go for software. That's why I'm kind of getting sloppy about math detail, because I think those details of math is not important, as long as you know how to do it using either software. But suppose if you refuse to use MATLAB, I guess you are in position that everybody expects you to know those math details. So now this is a statics class taught by a weird professor. So that professor is going to probably give you this kind of problem as a final, because this is going to actually lose your focus of why are you doing this program. I mean, this is not the math practice kind of exam. I want to check to see if you really understand the meaning of parallel axis theorem. So if I give you this kind of problem, I would probably give you, okay, do B and then set up the equation for A, because you know the answer for A. So if you can probably set up the equation of dix, and then you say, well, the rest of the math details, if I have a computer right here, I can do it in 5 seconds. Well, then it's good enough for me to give you 10 out of 10. So that's what I would do. I'm not going to probably give you like a tedious, detailed, long mathematical things. That's probably not the purpose of this class anyway. Yeah. But I expect you to know how to set up this. Anyways, any other question? Again, as you notice right now, section 4b, no matter what I do, the mathematics will show up. That's the strong motivation of me why using MATLAB for just about any solution of section 4b. I hope you kind of realizing slowly, hey, I think we need to put my hands on software. Or you spend tons of time doing just the mathematical details. Okay, it's essentially just a choice for every statics student. I faced that when I was a student. I basically said, well, no, I'm not the mathematician. I'm not going to do this. That was my solution. Okay. So here, homework. Determine the moment of inertia of the area about x-axis. Solve the problem in two ways, of course, yes. Using rectangular differential elements having a thickness dx and having a thickness dy. So this is exactly almost the same identical problem we did today. Okay, it's just a different function you deal with. Okay, so two different methods. You can do it. Okay. Now this problem is a very good exercise for you. Either if I'm not emphasizing enough, strong enough in this class, trying to make you use MATLAB, this is the homework that you should probably try using MATLAB to partially solve the problem, at least. Okay, I'm trying to motivate you. Okay, put your hands on your software. If the software is there, symbolic mass, and then as an engineer, you probably need it. That kind of skill set is needed. Okay, now is the time to kind of reconsider yourself, moving out of your comfort zone. Let's pick up a software available freely for you. It's part of your tuition. It's just to pick up MATLAB Symbolic Mass Toolbox and do this homework using that software. Okay. All right. Homework 432. Determine the moment of inertia of the area about the x-axis. Again, this is, oh yeah, there are two ways to do that. You can choose x and cut out the strip dx. Okay. Then integrate from x equal to 0 to 8-inch. That's one way. The other way around is you're going to choose y and cut out the strip dy, and integrate in the direction y from 0 to 2-inch. Either way. Which way did I do? Let me just find out. Homework 432, right? Oops, homework 432. Let me just double check. Oh, okay. Looks like I'm using x. It looks like it requires parallel axis theorem. In which, kind of similar to what we did today anyways. Okay, so you can handle that. This problem, mathematically speaking, well, it's not so bad actually. Oh, you can do this kind of math, do you? Integral of y cubed over 3 dx, and then what's the function? Y cubed is equal to x, so this is x over 3 dx. Oh, yeah, sure. You can integrate this kind of simple function. So if I choose to pick up a problem as a final exam, this could be one of them. Because you don't need a MATLAB for this problem. But of course, this one involves parallel axis big time. So the main focus of this type of problem is just how to set up your equation to begin with, and then math itself is very simple. Well, that kind of problem is an easy target for a final exam. Yes. Good hint. I appreciate your question. Okay. All right, so this is homework 432. Okay. All right, so page 8, composite area and product of inertia. Composite area is basically, suppose if you're given cross-section with a combination of a common cross-section, such as I-beam is composed of 3 rectangular cross-sections, 1 and 2 and 3. So you divide into 3 different parts, find out local moment of inertia using parallel axis theorem to determine the entire cross-section's moment of inertia about the given axis or a given centroidal axis of a given cross-section, either way. So this is a composite area. You can determine moment of inertia, and also let's just take care of the product of inertia, okay? So this is a composite area. You can divide into several parts, and each part is typically composed of simple rectangular shape, or it could be a cross-section circle or semicircle or something like that. Okay. And then let's just take a look at the product of inertia here. Product of inertia. I, xy. Okay. So the product of inertia is also a property of cross-sectional area rather than moment of inertia, which is the second moment of area. So moment of inertia is x squared or y squared. Product of inertia is x and y. Okay. So the product of inertia of an element of the area dA is essentially how much distance x or y away from each coordinate multiplied together. And then this is called the product of inertia. So remember, moment of inertia Ix is equal to integral over the area x squared dA. Moment of inertia Iy is integral over the area y, not the y. Okay? No, this is y. Sorry about that. Ix is y squared dA, so Iy is x squared dA. So those are the moment of inertia about x-axis and y-axis. This is product of inertia about coordinate x and y. Okay. So product of inertia is kind of interesting. Suppose if you have a body which has at least one axis of symmetry. So this is a symmetrical cross-section about coordinate x. If so, Ixy is 0. Product of inertia becomes 0 if you have at least one axis of symmetry of a body. Okay. So product of inertia is coming up. Suppose if you design an I-beam, and then which is not symmetrical at all. I mean, do you actually use that kind of stuff? I mean, not quite often you use that kind of stuff. So product of inertia is usually not quite important, at least in my own experience in the past. In structural analysis, product of inertia, is it going to be an issue? Usually not, because when you design a, structural frame of an airplane, do you choose an I-beam which is not completely non-symmetric in both x and y? I mean, it's a nightmare to manufacture anyways. And then what's the point of doing such a thing? So usually this doesn't come into play. So at least having one axis of symmetry gives you product of inertia becomes 0. If the product of inertia is non-zero, that means you are having a cross-section which is completely non-symmetric, very unique cross-section, which is rare, especially in structural analysis. Okay. So anyways, so obviously for the product of inertia, you can of course apply parallel axis theorem. Now, product of inertia involves both x and y. So this is parallel axis theorem or product of inertia. If you know the moment of inertia local about centroidal axis, this is oftentimes called IXYC. Okay. Now, IXYC for commonly given cross-section, such as rectangular cross-section or circular cross-section. Rectangle and circular cross-section, they have axis of symmetry. So IXYC for that case is, of course, 0. Okay. All right. So let's just take a look at a few example problems here. So this is composite body, example 441. Now, every time when I try to do composite body problem, okay, I always make a table. So this is called table method. I sort of keep doing this all the time. So this is my second nature, solving composite problem using table all the time. So this is what kind of thing? This is some kind of structure, C type of structure. Determine the distance x over bar to the centroid of the beam's cross-sectional area. Then find the moment of inertia Iy prime about y prime axis, which is centroidal axis. So this is a centroid. So first step is measured from here. This is a reference point. What is the location of centroid? Okay, so let's find out x over bar. And then after you find it, so what is the moment of inertia about this axis, centroidal axis? So this is two questions. So you have to have a table. First of all, the table to determine the location of centroid. I think you did it already. And then using that table, let's determine the moment of inertia. So I'm going to use two tables to solve this problem, okay? So let's begin with a sketch. So this is a given structure. Okay. So you can cut this in any way you want. You should have the same result. So I'm going to basically make it to 3 components. I'm going to add those 2 lines. So this is a part 1. This is 2. This is part 3. So you divide into 3 different parts. Each one of them is just a simple rectangular shape. Now, this is where you measure everything. So this is reference line, y-axis. Okay? And then you expect, here is the centroid. So this is the centroidal axis, y prime. Here is expected centroid. Okay? So what you're interested in is the distance x over bar measured from y to the location of centroid, y prime. So this is part thing. So this is the location of centroid, x over bar. Let's just find out. Now, each one of those parts have its own local centroid, of obviously. So this is the local centroid of part 1. This is the local centroid of part 2. This is the local centroid, part 3. So let's just determine the location of local centroid. What is this distance? Anybody?
Would be 80 millimeters.
80 millimeters, of course. Yeah, 120 plus 40 is 160 divided by 2, 80. That's correct. 80 millimeter to the local centroid of part 1 and also part 3. And also this. What's that?
20 millimeters?
This is a 20 millimeters. That's right. Half of the thickness. So those 3 are the local centroid locations. You already know. So let's just draw a table. Okay, so I do have part 1, part 2, part 3. And of course, summation. So first one is area A, which is, let's be careful. Area A, I'm going to use B times A. Okay? B times A, because later on, when you do a moment of inertia of rectangular cross-section, you know 1 over 12 BA cube, or B cube A, either way. So BA, that's the area. So part 1 is, area is 160 times 40, which is 6,400. What is the unit? Unit is millimeter square. Part 2, 40 times 80. This is 3,200 millimeter square. Part 1 is equal to part 3, 160 times 40, which is 6,400 millimeter square. So this is area of each part. If you add them up, you're going to have 16,000 millimeter square. Now let's find out next to the millimeter, which is a local centroid, which you already know. This is 80 for part 1 and part 3. Part 2 is 20. Then you do x to that times A, which gives you millimeter cube. So multiply this times that, 512,000. This times that, 6,400. This times that, 512,000. Add them all up, 1088. So what's this? 16,000, 1,088,000. Okay, anyways. So now you can determine the location of centroid x over bar, which is summation of x to the a divided by summation of a. So this is 1088,000 divided by 16,000. This is going to be 68 millimeters. 68 millimeter. Oh, okay, so this is 68 millimeter. So now we know centroid. Okay, so next step. I'm going to make up another table. Let's just zoom out a little bit. So another table consists of the following. So part 1, part 2, part 3, okay. So first of all, I want to find the dx. Dx is basically the magnitude of x to the minus x over bar. So that means, okay, so since I want to use the parallel axis theorem, I want to know first of all dx. We are going to do dx squared anyway, so negative positive doesn't matter. I just want to know the difference between x to the, which is each one of those parts, x to the is given. This is 80 millimeter for part 1. And then of course I know this x over bar is 68, okay? So this is going to give you very important information of parallel axis dx, okay? So this is magnitude of 80 minus 68, take a magnitude. I don't care about positive or negative. So this is 12. I'm going to take a magnitude of 20 and 68. This is 48. Some of them are positive, some are negative. I don't care because I'm going to take square anyway. So this is 80 minus 68, magnitude is 12. Okay, so this is one of those important information for parallel axis theorem. The other one is a local moment of inertia Iy prime over bar. This is 1 over 12 BA cube. Sorry, B cube A, sorry about that. B cube A. Okay. So you're going to look at the B and A information here of the area. So this is going to be, okay, 1 over 12, 160 cube times 40. I'm going to take the information straight out from here. This is B times A, B times A, B times A. So now it's B cube A, 1 over 12. So this is 1.365 times 10 to 7. The unit is millimeter force. Okay. Once again, 1 over 12, 40 cube times 80. This is 4.267 times 10 to 5. This is the same, 1 over 12, 160 cube times 40, which is 1.365 times 10 to 7. Okay, so we are ready to go for parallel axis theorem. Iy prime is summation of each one of those Iy prime over bar plus A times dy squared. So dx squared, sorry about that. Okay. So this is parallel axis theorem for each part. So this is going to be So part 1, okay? Part 1, Iy prime is 1.365 times 10 to 7 plus. Area A is 6,400 times dx squared, 12 squared, right? Plus part 2. Part 2 is this one, 4.267 times 10 to 5. Plus A is 3,200. Dx is 48 squared. Plus part 3. Part 3 is same as part 1. 1.365 times 10 to 7 plus 6,400 times 12 squared. Do you follow? If you compute it, 36.95 times 10 to 6 millimeter force. So composite parts computation could be super confusing if you don't use the table. So I always use the table. I always. Okay, so table is always set up in the same way, so that one of the key features here is when you try to find out the area, always b times a, because b times a can be used later, b cube a or b a cube, either way. So it's easy to kind of line up. Okay. The other one is, of course, dx is going to be squared anyways. So minus or plus doesn't matter because you take the square. So I always ended up having, okay, so what's the difference between x tilde and x over bar? Take a magnitude only. Because it's going to be squared anyways, minus or plus, it doesn't matter. Okay. This is the local moment of inertia for each part, 1 over 12 b cube h in this case, because it's rectangular shape. Okay. And then the rest is, of course, you're going to sum them up. If you have 5 different parts, you have to sum them up 5 different parts. So using table, you're going to significantly well, it's not simplify, but you're going to basically keep everything in order. Otherwise, it's going to be easily be chaos in your note. You basically lose in the middle of the process. What am I doing here? Kind of. Okay, go ahead.
So we use the parallel axis theory
Yeah.
at the end, right? So why is it Iy prime and not just Iy? Isn't that what the point of the parallel?
Yeah, because now y prime is a centroidal axis.
Oh, okay, I got it.
Yeah, that's right. So this is the original coordinate, but it's not the centroidal axis. Now I want to know the centroidal moment of inertia of this entire cross section. That's why. Okay. So let's be careful about the terminology or definition. I think I'm going to probably really need to emphasize a few important things. So in this case, x over bar really means centroid of the cross section and then x tilde is local So those are both measured from coordinate x, I think. Right, no, y, sorry. 5 more minutes. So those are both measured. Measured from y. But the y is not the centroidal axis. Y prime is centroidal axis. That's what I want to have. Okay. So this Iy prime over bar, this is a local centroidal axis. In other words, what is the moment of inertia of the local centroidal axis? That's Iy prime over bar. This is essentially 1 over 12 b cubed a. Okay. So this actually probably making you think a little bit. So again, homework 441. this is only two parts. So you're going to make a table which is much smaller than the table today we made. But yes, this is going to make you think, okay? I can easily create final exam problem out of this homework. How? I can basically say, okay, find the moment of inertia I y prime about y prime centroidal axis. I can easily create a variant of this problem. I can easily create a variant of this problem. Oh, this problem doesn't start. Okay. So again, it may take some time to kind of think about it, but making a table probably making more sense. That's what I started when I was a student. I keep doing the same thing. Without the table, this problem is chaos, completely. You probably lose in the middle and saying, okay, where am I? Okay. So let's just stop here today. So coming back tomorrow tomorrow is the last day of the class. We are going to finish up a few more examples of Unit 4B, and then we're going to do a quiz, probably the very short lecture tomorrow, and then let's just start doing quiz early, and let's just get ready for the final. Any question? Have a good day, and then see you back tomorrow.